Hello, everybody. Let's talk through the solution to the in-class problem, and then let's talk through the solution to some variations on that problem. So the context was we've got a ball whose diameter is 5 feet, and it's rolling without slipping along the ground, and it makes one complete revolution every 30 seconds, and we want to make a vector equation that traces the path of a point on the perimeter of the ball. And so we talked about breaking it into three different vectors. This vector that sticks straight up, that doesn't move with time. So if the ball's diameter is 5 feet, that vector just points up 2.5 feet. And then we have a vector that's just stretching rightward. So let's make a vector that gets longer and longer and just faces right, but it'll be at the wrong speed. So here 1, 0 just faces right, and here it's getting longer with time, but probably not at the speed we want. And then we have this vector that goes from the tip of those two, like those two point to the center of wherever the ball is. And then the third one should be the radius of the circle, and it should just rotate. So let's do that. The radius is 2.5, and it's going to rotate. And this one is also going to be a little bit wrong, and then we'll fix it. Okay, so a couple things that we need to figure out. This is about our horizontal speed. This is about our rotational speed. So let's tackle these pieces separately. The horizontal speed, so let's see, I make one revolution every 30 seconds. If you think about a ball rolling, it makes one full revolution when its entire circumference has touched the ground once. So this horizontal distance should be the same as the circumference of the ball. So let's solve for that. Circumference is 2 pi r. Twice r is going to be 5 feet. So the circumference is 5 pi. And if I think about speed, speed is distance over time. So if I went, 10 feet in 3 seconds, it would be 10 over 3 feet per second. So here I'm going 5 pi feet. That's my horizontal distance. It's taking me 30 seconds. So I know my horizontal speed should be 5 pi over 30 feet per second. So a great thing to do is let's just make that the multiplier on t out here. Because if you think about it, if I said 2t times 1, 0, when t is 1, I will go a horizontal distance of 2, because it'll be 2 times 1 times 1. When t is 2, it'll be 4. When t is 3, it'll be 6. So you can think about this as saying with each second increase, we are stretching the vector to the right an additional 2 units. So if this speed is 2, I really want my speed to be 5 pi over 30. So let's write that. So t times, I'll put it on the inside of the vector here, 5 pi over 30, 0. And like just a spot check, let's imagine if I plug in time as 0, then this scales down to be length 0, which is what it should be because I haven't moved to the right at all. If I plug in time 30, then I'll have 30, and then this divides by another 30, so those will divide to make 1. And I'll be left over with a horizontal vector of 5 pi, which is exactly the right horizontal distance. Great, so I know I've solved for my horizontal speed correctly. Let's think about rotational speed now. So my rotational speed, let's see, I go one revolution every 30 seconds. What is one revolution? As an angle, one revolution is 2 pi. So I know I want to go a full 2 pi every 30 seconds. So I could write it this way. I could say cosine 2 pi over 30t. Let's just imagine the cosine part for a minute. And same thing, if I plug in 30 as the time, 30 divides 30, and I'm left with cosine of an angle of 2 pi. So that means when time is 30, my angle is 2 pi as I want it to be. Except the problem is I don't actually want it to be 2 pi, because 2 pi would be an angle facing to the right. It would be a full rotation, but facing to the right. And actually, I want my starting angle to be up here at pi over 2, and then I want my angle to decrease until eventually it gets back around to, I guess, negative 3 pi over 2. So we talked about this two ways at the end of class. One way we could do it, zoom out here, one way we could do this would be the following. If we want our angle to decrease, we'll put a negative sign here in front. And the problem is if I plug in time equals 0, I'm still getting an angle of 0. And so we could add an angle of 2 pi to shift the angle up when time is 0. So our final angle would be something like this. Let's cross this out. Our final angle would be cosine negative 2 pi over 30 t plus pi over 2. And a good way of thinking about that, again, is let's plug in time equals 0. At time 0, this inside angle just becomes pi over 2, which points up, which is what we want. And then 30 seconds later, we'll still have that pi over 2, but it'll be pi over 2 minus 2 pi, which makes sense because if I subtract 2 pi, that's like saying subtract a full rotation, which is what I want the angle to be 30 seconds later. So I could say 2.5 as my scale factor times cosine this and sine the same thing. And all of the rest is the same. So I'd have time times 5 pi over 30 comma 0, and then here I'd have 0, 2.5. And that's it. Okay, so let's solve some variations on this. Or actually, I'll stop the video here and we'll do a different video on the variations.